Hi everyone, my name is Davi. I'm a postdoc researcher at Unicamp, and today the work that I'm going to present is about impacts of modeling advanced physical phenomena in a fractured carbonate reservoir subject to WAG-CO2 injection. So what does matter when modeling WAG-CO2? We know that water alternating gas injection has been used in industry as an enhanced oil recovery method for decades, and but we need to go deeper on understanding physical phenomena that may be important when modeling this type of recovery method. So the first point is to use a compositional method, as we have a change in compositions and component compositions in all the phases, and so this compositional models makes the model more accurate because it considers the mass balance is more accurate. And then we have dual portal pair modeling. It's also important. In our case, we have a fractured reservoir. So it's important to consider these two different medians and to connect these grids, to connect these medians. And these two topics by themselves, these two first topics by themselves make the model more time consuming. Then we have this advanced physical phenomena, matrix fracture transfer calculation, relative permeability hysteresis, solubility in aqueous phase, molecular and gas phase diffusion, and velocity dependent dispersion. And we have this trade-off between time cost and accuracy, and that's what I'm going to present. I want to show you what is relevant or not in our case. So I'm going to present each phenomena at a time, how I applied it, and the results. And the first one is the matrix fracture transfer model. So this phenomena is related how the mass transfer, the effects that are considered on the mass transfer between the matrix and fracture in the same grid block. So we have neutron zero as the simplest model. It doesn't consider gravity effects, capillary effects, or any other, and it's the one that was applied in Instinct 2. Then we have Neutron 1 that accounts for gravity segregation. Neutron 2 accounts for capillary effects, and finally Neutron 3 accounts for a correction of transfer surface area. I want to get your attention here because by now we have used Neutron 0, the simplest model in Instinct 2, but the default in SMG is Neutron 3. So how impactful is the phenomena? How impactful is these models? Here we have the results. And I applied these models in an ensemble of 197 geostatistical reservoir scenarios under uncertainties. And we can see that we can see the risk curves. The blue one is for the simplest model. Then we have orange one considering gravity effects, and we see that we have a substantial deviation from the simplest model. The capillary effect is not that significant, and when we add this correction for the transfer surface area, this deviation becomes lower, but it's still significant. We have that sweep efficiency is improved with this model, more advanced models, and in the figure on the right, we see a more gas concentrations on the upside layers, and also the water is more spread around the super K layers. So it confirms, it shows us why the sweep efficiency is better. And for the next phenomena, I'm going to present the results for both models, for both Neutron 0 and Neutron 3. So here we have the results for other field indicators. And we see that in the default model, Neutron 3 improves NPV. We have this trend of higher oil production, higher water production, higher water injection, and a lower gas production. And we see that the risk curves for gas production and water production, the deviation is very significant. The increment on simulation runtime in a base case was only 1.1 time. So we have here very, very important phenomena that does not make the model much more time consuming. Now about the impact of hysteresis in relative permeability curves. I presented a work last year on this topic, on this phenomenon. And my idea here is just to compare hysteresis with the other phenomena and to show the impacts of hysteresis coupled to neutron 3. And we have two hysteresis scenarios: hysteresis only in low permeability grid blocks, and hysteresis in low and high permeability phases. So in Super K, I considered very low values for hysteresis parameters, and we are going to see the results. So here we have the results for hysteresis. The first figure is comparing with the model without hysteresis, considering neutron 0. And for this scenario and for this production strategy, we have a lower NPV, lower in oil production, and much lower gas production. But the results could be different for different scenarios, for different production strategies. And the second figure shows the impact of neutron 3, and it shows a lower gas production and a higher water production. And we can see that there's a difference between the model with the LK scenario and LSK scenario. When we couple both, we consider both phenomena, we see that the effect in terms of NPV is almost zero for LK scenario. And that's because the impact of hysteresis is negative, while the impact of neutron 3 is positive. So when we consider both phenomena, the deviation in the NPV is almost zero. But when it comes to gas production, both phenomena give us lower gas production. So the effects add up, and we have a very small, very lower gas production. The third phenomenon studied was solubility in aqueous phase, and I used the Harvey's correlation variance constant. In this model, solubility is in function of pressure, temperature, and salinity. And we have that CO2 solubility is higher than hydrocarbon solubility in aqueous phase. So in this study, I have two situations. The first, CO2 solubility only, and the second one, I considered both CO2 and methane solubilities in the model. So the figure on the left shows the CO2 content in production flows, and dotted line referred to the model without solubilities, full line referred to the model with CO2 and methane solubilities. And we see that the CO2 content in gas and oil phases is lower, and the CO2 content in aqueous phases is higher. So one could say, okay, this phenomenon is not that important in terms of oil production or NPV, but when you're talking about CO2 emission, it's very important, because in Unison 2 we have this recycling premise. So all the produced gas goes back to the reservoir, but not all CO2. CO2, part of an important fraction of CO2 is being produced in the liquid phase. So the figuring on the right shows that the CO2 global mole fraction is much higher in the model without solubility, and the CO2 global mole fraction after the production period left in the reservoir is much lower when we consider CO2 solubility in our models. So in this slide, we can compare the impact of solubility and the neutron 3, and we see that the impact of neutron 3 is much more substantial. When we consider both of them, it prevails the impact of neutron 3. And also we observe in the first figure that solubility decreases gas production and increases water production. and this deviation could be explained by changes in densities. As we have CO2, now we have CO2 in liquid phase, in water phase, then we have a denser phase. Now, what about molecular and gas phase diffusion? We have different models that could be used for molecular diffusion in oil phase, gas phase, and we also could, instead of using a model, we could input the diffusion coefficient. So I use the sigma correlation for oil and gas phase, and I input the diffusion coefficient for in the aqueous phase. And also we have this gas phase diffusion. It's an optional phenomenon that we can include in the model. According to the manual, it could be important. When we have fractured reservoirs, but we don't have many data on the literature about these diffusion coefficients. So I extrapolated a little bit these coefficients to trying to see if it could be important, relevant or not. And when we look at the results, we see that impacts of diffusion, both molecular diffusion or gas phase diffusion, are not substantial when compared to Anitron 3. So yeah, the increase in computational time is more significant than the impact on the field indicators. So this, for our case, molecular and gas phase diffusion is not an important phenomenon. The last phenomenon is the velocity-dependent dispersion. And dispersion is the mixing of fluids caused by diffusion, local velocity gradients, locally heterogeneous streamline lengths, and mechanical mixing. And it could be applied in a longitudinal flow direction or in a transverse flow direction. I also considered a tool available in CMG for numerical dispersion to avoid a numerical dispersion. So here we are talking about physical dispersion. Here we have the equation for dispersion, and the term that is related to the diffusion is null in this case because I'm not considering diffusion. So I performed some sensitivity analysis to investigate its dispersivity effect, and what we can see in the figure on the left is that its dispersivity increases oil production and gas production and decreases water production. And in the figure on the right, when I keep the same transverse dispersivity value and I change longitudinal dispersivity, the deviation on oil recovery is very small. But when I do the opposite, when I keep the same longitudinal dispersivity and I change transverse dispersivity, then the deviations are higher. So in a nutshell, what do we have here? Dispersion promotes a very sweep efficiency, and transversal dispersion is more impactful. Here in this slide, in the first figure, we have the model without dispersion, and the figure below we have dispersion. And what we can see in these figures is that the effect of dispersion is higher in regions surround super K. So this phenomenon is important, it's kind of interesting in our case because of super K. In this region, we have high velocity gradients, and that's making this phenomenon more relevant in our case. And when we compare the impact of dispersion and impact of neutron 3, we see that in terms of NPV, oil production, the impact is of the same magnitude, about 2% each one. But the impact of neutron 3 in gas production and water production is much higher. And when we consider both phenomena, we see that the NPV increased 4%. So dispersion could be considered important in this case. Now to sum up, we have first for matrix fracture transfer models, we have that gravity effect is very important, promotes oil transfer from matrix to fracture. The use of the simplified transfer model NTran0 shows potential risk of obtaining an accurate result. And NTran3 is the default model and can lead to better results in optimization process. And even could promote WAG as a more advantageous method than water flooding in Unicamp 2. In terms of hysteresis, I showed you that both phenomena combined were not as impactful, but for other strategies or other scenarios, we have that hysteresis can contribute to oil recovery. So in these cases, both combined could lead to substantial change in the results. For CO2 and methane solubilities, we have not a substantial change in NPV or oil recovery, but we have an increase in CO2 produced in the liquid phase. Now, molecular and gas phase diffusions are not a relevant phenomena for our case. And finally, velocity-dependent dispersion gave us a change of 2% on the NPV, but it could be more impactful in geological scenarios with higher super K densities. So I hope this work gave you some insights or make you to understand a little bit more about the important phenomena that are involved in WAG-CO2 injection. And I thank you all the institutions that supported the work and all of you that watched the video.